All right, this says, suppose you use the second degree Maclaurin polynomial to approximate cosine of 0.5. It says, give a bound in the error for the approximation based on A, the alternating series error bound theorem, and B, the Lagrange error formula, which we also call the remainder estimation theorem. All right, so in BC Calculus, you have 2 error tests in this chapter, and this is just meant to get you practice with both and tell you can use both in a situation like this. This situation being like the cosine Maclaurin series is an alternating series, so you can use either the alternating series test, which is probably much quicker, or the Lagrange error formula. The Lagrange error formula works regardless of whether your series is alternating. Okay, but let's recall, like cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc., right? That's its infinite, that's an infinite series that represents cosine. So let's do our alternating series test here. Okay, that one's easy to apply. Alternating series, error bound. Theorem. So that one's pretty simple. So we're using the degree 2 here, right? So we're using it to approximate cosine of 0.5. So like if I replace 0.5, if I replace x with 0.5, then I'll get this. Right, I'm going to get this infinite series that converges to cosine of 0.5. And what they're asking up here is like, let's say you wanted to use the second partial sum, or the second degree polynomial. So that would just be this, right? So the question is like, if you're going to do this, how far off are you? Right? How far off is this from actually the true value of cosine of 0.5? And the error test is really easy. So for an alternating series, if you're going to use the alternating series test. So our error, let's use good notation here. So our error, cosine of 0.5, the true value minus our approximation, is not going to be more than. So the alternating series test, just look at the next term, right? What's the next term here that we didn't use? 0.5 to the 4 divided by 4 factorial. Okay, we looked at that graph in class. It's an easy test. Just look at the next term that would have appeared, and your error is less than that. And so let's just go see what that actually is. So that's like 0.00, what did I say to round to? I probably said to round to, I guess, millionth. So then we're going to write down 0.002604. 0.02, okay, so that's equal to 0.002604. Okay. Also, like I think this is implied in the question over here, or asked, in the alternating series, the last term is positive, right? Like the last term we used here was negative, right? The last term being this. So that must mean like we're a little below the true value, like we're at the left side of the limit. So the last term is negative. Okay, the last term in the approximation is negative. Right, the negative 0.5 squared over 2 factorial. So that must mean that it will be too small. Okay. Okay, we under-approximated. I'm going to unsplit screen for a minute. All right, so there's our alternating series test. I'll fill in the blanks in a minute. All right, that's very simple to apply, right? You get two things. You get the error by looking at the first unused term, and if the last thing you did was subtract, you under-approximated. The last thing you did was add, you over-approximated. Now let's do the Lagrange error bound. Lagrange error bound. Okay, also known as the remainder estimation theorem. They just go by that. We'll just, for our purposes, it's the same theorem. Okay, now what that would say is, right, it's this formula. When using the nth degree Taylor polynomial, okay, your error is not going to be more than this formula, where m is the maximum value, of the n plus first derivative of your function on the interval 0 to wherever you're approximating, or a to where you're approximating. So the center to x. Okay, now in our case, we're going to say, so n, so they told us specifically to let n be 3. So that's because if you go back up here, like if you look at the, let's go up here. So you see how cosine, so like what's missing here is the degree, if the degree 4 term looks like this. So the degree 3 term gets skipped, but you can kind of think of it as really being there, just plus 0x cubed. So the degree 2 polynomial is also the degree 3. And using a degree 3 gives you a little more precision, or viewing it as a degree 3 gives you a little more precision, so that's why it's sometimes done. So we're going to let n equal 3. Our center is clearly 0. Right, our center is clearly 0. And we're approximating it at 0.5. And for m, we want the maximum value for us of the, right, this is the maximum of the fourth derivative. It really should be actually also an absolute value, but it's the maximum of the fourth derivative of cosine. So let's just find that, right? So cosine, and then the first derivative is negative sine, the second derivative is negative cosine, and then the third derivative is sine, the fourth derivative is cosine. Okay, so this is just, okay, and that'll never be bigger than 1. We usually use 1 for the sine and cosine ones. That'll be fine. Okay, so let's see. I've got that my error R3 of 0.5. The error when approximating the function at 0.5 would be 1 times absolute value of 0.5 minus 0 to the 3 plus 1 divided by 3 plus 1 factorial. And that's 0.5 to the 4th divided by 4 factorial. Actually, that's like, happens to be exactly what we got up here, right? So I don't really need to, that doesn't always happen, but it did here. 0.002604. All right, so putting that all in, it says, this is a scaffolding problem to get you to kind of piece the ideas and get the language together. The error will be at most the absolute value of the next unused term, which is 0.5 to the 4th divided by 4 factorial, which is to the nearest millionth about, so 0.002604 is what we said. Using the Lagrange error formula and viewing the second degree as a third like we did, we get the error that is to the nearest millionth at most. So we got the same thing, right? Just copying this down. Since this is an alternating series, the last term in the approximation is negative, and the negative. The approximation will be, we said, too small. So the point of this problem is to remind you there are two error tests we use, and if it's an alternating series, just use the alternating series test because it's quicker. But the Lagrange error one works no matter what, whether your series is or polynomial is alternating or not. And a good ultimately they tell you the answer, or they tell you which one to use. That's kind of ideal, but this hopefully kind of glues those things together in your head.